The thought you are having right at this second, the quiet voice reading along with me, may not be only chemistry inside your skull. There is a serious theory in physics, proposed by a Nobel Prize winner, that says each conscious moment is a tiny collapse of quantum possibility, triggered by gravity, woven into the same fabric of spacetime that bends light around galaxies. If that sounds impossible, good. Tonight we are going to take it apart slowly and honestly, and find out exactly how much of it the evidence can carry, and where it quietly falls apart. So get comfortable, settle in, and subscribe if you'd like to come along. The strangest place in the universe might be the inside of your own head. Part 1. The strangest thing you'll ever be told about your own head. I want to begin tonight with a thought, and I mean that almost literally. The thought you are having right now, this very second, the quiet inner voice reading these words along with me, the faint sense that there is a you somewhere behind your eyes, listening. Hold on to that feeling for a moment, because there is a theory in modern science, a real one, proposed by a man who later won the Nobel Prize in Physics, which says that the thought you are having is not only a flicker of chemistry inside your skull. It says that thought is a physical event woven into the same fabric of space-time that bends light around galaxies and holds the stars in their slow orbits. It says, in plain language, that your mind and the universe are not two separate things at all, but the same thing, briefly folded into a shape that can wonder about itself. That is an enormous claim, and I am not going to ask you to believe it. I am going to ask you to do something more interesting than believe it. I am going to ask you to follow it, slowly, all the way to the place where the evidence runs out, so that by the end of tonight you understand exactly how much of this astonishing idea the science can actually carry, and exactly where careful thinking gives way to wishful thinking. Because both of those places are worth knowing, and the border between them is one of the most fascinating boundaries in all of human knowledge. Most of us carry around a quiet assumption about what we are. We assume that the mind is, when you get right down to it, just the brain doing its job. Neurons firing, signals racing along wet biological wires, chemistry sloshing across tiny gaps, and somehow, out of all that electrical traffic, the feeling of being alive emerges, the way a song emerges from a radio. It is a comfortable picture, and it explains a great deal. But there is a theory that looks at that comfortable picture and says it is a little like calling a cathedral just a pile of stacked stone. Technically true, and yet it misses the thing that actually matters. The thing that makes a cathedral, and not a quarry. The theory has a name, and I am going to say it once now, and then take it apart so gently that by the end, the name will not intimidate you at all. It is called orchestrated objective reduction. Scientists who work on it shorten it to OR. Every word in that name is doing real work, and over the next couple of hours, we are going to unpack each one until it makes sense, until you can hold the whole strange machine in your mind and see how the pieces fit. For now, just let the name sit in the room with us, like a guest who has arrived early and is waiting patiently to be introduced. Here is the contract I want to make with you before we go any further, because honesty matters more on this subject than on almost any other. This is not mysticism. This is not a wellness slogan or a comforting story dressed up in scientific words. This is a genuine, peer-reviewed, fiercely argued scientific theory put forward by Roger Penrose, one of the most respected mathematical physicists alive, working with an anaesthesiologist named Stuart Hameroff, who spent his whole career studying how consciousness gets switched off. And it is also a minority view. Most neuroscientists do not accept it. Some think it is almost certainly wrong. So, I am going to give you the real thing, the strong version of the claim and the strong version of the objections, and I am not going to tilt the scales. By the time you fall asleep, you will be able to make up your own mind, which is the only kind of mind worth making up. The single question we are going to circle all night is this: is a conscious moment one frame of your experience, a tiny collapse of quantum possibility, triggered not by a scientist with a measuring device, not by an observer, but by gravity itself, happening roughly 40 times every second behind your eyes? That is the spine of everything tonight. Every fact, every detour, every objection is going to hang off that single question like ornaments on a thread. Let me tell you the shape of the climb, so you always know where we are. First, we are going to look at why the ordinary explanation of consciousness, the just neurons story, quietly fails, and why that failure left a door open for something stranger to walk through. Then we are going to meet the two unlikely people who walked through it, and the two ideas they carried. After that, we go inside the neuron, far smaller than you have probably ever pictured, to find the hardware the theory depends on. Then comes the most audacious idea of all, the one where gravity pulls the trigger. And then the trial begins in earnest, the case against the theory and the case for it, the experiments that nearly killed it and the experiments that dragged it back from the dead. We finish by asking what it would all mean for you, for thinking machines, and for the universe's strange habit of producing creatures who can ask where their own awareness comes from. I want to leave you with one promise to carry up the climb, because it is the part that genuinely keeps me awake. If this theory is right, then the link physicists have hunted for over the last century, the missing bridge between the quantum world of the very small and the gravity that shapes the cosmos, would not first reveal itself in a black hole or in the first instant of the Big Bang. It would reveal itself here, in something warm and ordinary and close, in the dozens of small collapses happening inside your head between one breath and the next. The deepest law of the universe, hiding in the most familiar place there is. So settle in, get comfortable however you like, to get comfortable when you are going to be here a while. There is no rush tonight, none at all. The universe has kept this particular secret for 13.8 billion years, and it is not going anywhere before morning. You will not need any mathematics to follow me. You will need only your curiosity and a willingness to let one comfortable assumption come quietly loose. Because before we can take seriously the idea that a thought is a cosmic event, we have to understand why the simple story, the one almost everyone believes, was never quite enough to explain the one thing it most needed to explain. And that gap, that small persistent crack in the machine, is where our whole journey begins. Is less than break time equals 1s, is greater than number. Part 2. The crack in the machine. Let us start with the picture almost all of us inherited, because it is a good picture and it deserves respect before we go looking for its flaws. The brain, in the standard view, is an electrochemical computer of staggering complexity. It contains around 86 billion neurons, each one connected to thousands of others, and these neurons communicate by firing tiny electrical pulses and squirting chemicals across the gaps between them. Thought, memory, perception, the whole churning theatre of your mental life is built from patterns in this firing. Show someone a face, and a particular constellation of neurons lights up. Recall a childhood smell, and another pattern flickers awake. This model is not a guess. It is supported by mountains of evidence, brain scans, electrode recordings, the precise and tragic effects of strokes and injuries. When a specific region is damaged, a specific ability vanishes. The mind, clearly, is bound up tightly with the physical brain. Nobody serious disputes this. And yet, there is a question this picture cannot touch, and the question is so simple that children sometimes ask it before they learn they are not supposed to. Why does any of it feel like anything? Why is there something it is like to be you? A philosopher named David Chalmers gave this puzzle its modern name in 1995. He called it the hard problem of consciousness, and he called it hard for a precise reason. He pointed out that science is very good at what he called the easy problems, and by easy he did not mean simple, he meant solvable in principle. How does the brain distinguish red light from green? How does it store a memory, control a hand, direct attention? These are mechanisms, and mechanisms are exactly the kind of thing science knows how to chase down. But there is one more question that refuses to behave like the others. Why is all that mechanism accompanied by an inner experience? Why is there a private, felt quality to seeing red, instead of the brain simply processing the wavelength in the dark, with nobody home? Let me make this concrete with a thought experiment, because it is the kind of thing that sounds abstract until you actually try it. Imagine that science has finished. Imagine we have a complete, perfect map of a human brain in the act of looking at a red rose. Every neuron accounted for, every firing time to the millionth of a second, every chemical traced. We could hand that map to a scientist who had never seen red, who had lived their whole life in a black and white room, and they could read every line of it. And here is the unsettling part. Nothing in that map, no matter how complete, would tell them what red actually looks like. They would know everything about what the brain does, and still know nothing about what the experience is. The map describes the machinery perfectly and says not one word about the feeling. That gap between the full physical description and the felt experience is the hard problem, and it has not gone away in the 30 years since it was named. If anything, it has only grown more stubborn. Now, why does this matter for our story tonight? It matters because of what it implies about computers. On the standard view, consciousness is just a certain kind of information processing. And if that is true, then it should not matter what stuff the processing is made of. A brain made of neurons, a computer made of silicon, a machine made of gears and string. If they all run the same pattern of information, they should all be equally conscious. The substance would be irrelevant. The pattern would be everything. Many extremely smart scientists accept exactly this, and it is the quiet assumption underneath every conversation about whether an artificial intelligence could one day truly wake up. But Roger Penrose looked at this assumption and refused to accept it. He suspected that the felt quality of experience is not just a pattern that could run on anything, but something that depends on the actual physical process going on, something tied to the specific, peculiar physics of the real world. This is the fork in the road, and I want to plant it firmly now, because everything later branches from it. On one path, consciousness is substrate-independent computation, a pattern that could in principle run on any sufficiently complex machine. On the other path, consciousness is a specific physical process, tied to what the brain is actually made of and the particular laws that govern it, something a simulation could imitate from the outside, but never actually be. Almost the entire mainstream of neuroscience walks the first path. The theory we are exploring tonight walks the second, and it walks it all the way to the strangest destination in modern science. I want to be fair to the mainstream, because it is full of brilliant, careful work, and dismissing it would be both rude and wrong. There are serious, respected theories of consciousness that need no quantum physics at all. One, called global workspace theory, pictures consciousness as a kind of broadcast, where information becomes conscious when it is shared widely across the brain, lit up on a central stage for all the other processes to use. Another, called integrated information theory, proposes that consciousness corresponds to how tightly a system's information is woven together, a quantity it tries to measure directly. These are sophisticated, evidence-driven ideas, and they explain real phenomena. But notice what every one of them leaves untouched. They describe the conditions under which consciousness appears, the architecture and the dynamics, and they remain almost entirely silent on the original hard question, why is any of it felt at all? They tell us when the light is on, they do not tell us why there is a light. So here is where we stand at the edge of the crack. We have a magnificent machine, the brain, whose workings we understand better every year. And we have one stubborn, irreducible mystery sitting right in the middle of it, the mystery of why the machine has an inside, why there is an experience rather than just a process running in the dark. Into that gap, that vacancy the ordinary story cannot fill, a stranger and bolder idea came rushing, and it arrived, carried by two people who, by every reasonable expectation, should never have ended up working together at all. One was a mathematical physicist obsessed with a famous theorem about the limits of logic. The other was a doctor whose entire profession was the daily, practical art of switching consciousness off and on. How those two found each other, and what they built when they did, is where the real story begins. Is less than break time equals 1s is greater than. Number, Part 3. The Mathematician and the Anaesthesiologist. Let me introduce you properly to the first of our two figures, because his credentials matter enormously for how seriously we should take what follows. Roger Penrose is not a fringe thinker shouting from the sidelines. He is one of the towering mathematical physicists of the last 100 years. In the 1960s, working alongside Stephen Hawking, he proved theorems about black holes and the structure of spacetime that reshaped our understanding of gravity. And in 2020, he was awarded the Nobel Prize in Physics for that very work. When a man like this tells you that the explanation of consciousness requires new physics, you cannot simply wave him away as a dreamer. You have to at least sit down and hear him out, even if you suspect in the end that he is wrong. And here is the thing that surprises almost everyone. Penrose did not arrive at the idea of quantum consciousness through anything mystical or spiritual. He arrived at it through cold, hard logic, by way of one of the most famous results in all of mathematics, Gödel's incompleteness theorems. Now, I promised you no mathematics tonight, and I will keep that promise, so let me give you the spirit of it rather than the machinery. In the 1930s, a logician named Kurt Gödel proved something shocking. He showed that in any formal system of rules powerful enough to do ordinary arithmetic, there will always be true statements that the system itself can never prove. There are truths that lie forever beyond the reach of the rules. The rules can never catch them all. Penrose took this result and asked a daring question. He noticed that human mathematicians can often look at one of these unprovable statements and simply see that it is true, can understand its truth in a way that the formal rules never could. And he reasoned, if a human mind can grasp truths that no fixed set of rules can prove, then perhaps the human mind is not running on fixed rules at all. Perhaps thinking, real understanding, is doing something that no algorithm, no step-by-step computation can ever do. He gave this a name. He called it non-computable. The mind, Penrose argued, does something non-computable, something no ordinary computer following instructions could ever reproduce. This was a thunderclap of an idea, and it leads somewhere very specific. If the mind does something no computation can do, then whatever the brain is using to think cannot be ordinary computation. It has to be a physical process that is itself non-computable, a process that does not just follow rules but somehow steps outside them. And when Penrose surveyed all of known physics, looking for any place where the rules genuinely break down, where the future is not simply calculated from the past, he found exactly one candidate. He found the moment of quantum collapse, the still unexplained instant when a particle that had been in many possible states at once suddenly becomes just one. That moment, he realized, is the one place in all of physics where our equations stop being able to tell us what will happen next. That mysterious gap, he proposed, might be where the mind lives. He laid all of this out in a book in 1989 called The Emperor's New Mind, and it caused an uproar. Here was a Nobel-caliber physicist arguing that consciousness could never be captured by computers, that it required physics we did not yet understand, hiding in the unexplored borderland between quantum mechanics and gravity. The argument was bold, and the writing was brilliant. But there was a gaping hole in it, and Penrose knew it perfectly well. He had a physics idea with no biology to hang it on. He had no answer to the most obvious question of all. Where, in the warm, wet tissue of an actual brain, could anything as delicate as a quantum state possibly be held? He had identified the kind of magic he needed. He had no idea where in the body to find the magician. And this is where our second figure walks onto the stage, from a completely different direction, carrying the missing piece without even knowing the locket would fit. Stuart Hameroff is an anesthesiologist. For decades, his job was to stand in operating rooms and, with a careful dose of gas, reach into a conscious human being and switch their awareness off, then bring it safely back hours later. Think about how strange that profession actually is when you stop to consider it. An anesthesiologist is someone who has practical, daily, hands-on control over the very thing philosophers cannot even define. They turn consciousness off the way you turn off a lamp, and they have been doing it for over a century, and here is the unsettling truth at the center of the whole field. Nobody has ever fully understood how anesthesia actually works. We can do it reliably without knowing why it works. Hameroff spent his career chewing on exactly that mystery, and he noticed a clue that had been hiding in plain sight. Anesthetic drugs are chemically all over the map. Some are gases, some are more complex molecules, and they look nothing like one another. By all rights, such different substances should work in completely different ways, and yet they all produce the same single effect, the clean erasure of consciousness, while often leaving much of the rest of the brain's activity humming along. How could so many different keys open the same one lock? Hameroff followed that question, and it led him to a structure inside the cell, a structure most biologists regarded as little more than scaffolding. He found that these chemically diverse anesthetics all seemed to gather in the same tiny oily pockets, and that some of those pockets sat inside slender protein tubes, called microtubules. He began to suspect that consciousness was not happening out in the wiring between neurons at all, but somewhere deeper, inside them, in those overlooked tubes. Then Hameroff read Penrose's book, and something clicked into place that neither man could have managed alone. Penrose needed a place in the brain delicate and orderly enough to shelter a quantum state. Hameroff had spent years staring at exactly such a place, a structure built with the kind of precise, repeating geometry that might, just might, protect something quantum from the chaos around it. Hameroff wrote to Penrose. They met, and out of that meeting came a single combined theory, with the mathematician supplying the cosmic trigger, the gravity, and the spacetime, and the anesthesiologist supplying the location in living tissue where that trigger could be pulled. Two halves of an idea, carried by two people who each held only one half, finding each other across the gulf between mathematics and medicine. I want to be honest with you about where this leaves us, because the honesty is the whole point tonight. Two serious credentialed people proposing a bold theory does not make the theory true. The history of science is littered with brilliant minds who were confidently, magnificently wrong. What it does mean is that we owe the idea a fair hearing, a genuine trial, rather than a dismissal. And to give it that trial, we have to do something we have never done together. We have to shrink ourselves down, far past the neuron, far past anything you can see, into a hidden architecture inside the cell, and meet the strange little structures that Stuart Hameroff staked his entire scientific reputation on. Because if the secret of consciousness really does live somewhere in the body, this theory says it lives there, in a place so small that until recently almost nobody thought to look. Is less than break time equals 1s, is greater than number, part 4, the forest inside the cell. We are used to a certain stopping point when we zoom into the body. We go from the whole person to the organ, the brain. From the brain we go to the neuron, that branching cell with its long tail and its tangle of connections. And there, usually, we stop. The neuron feels like the bottom floor, the basic unit, the atom of thought. But it is not the bottom floor at all. A single neuron is less like a switch and more like an entire city, a churning metropolis of structures and machinery. And tonight's theory says the real action is not the city itself, but something woven through its streets, far smaller, almost unimaginably fine. So let us keep going down, past the neuron, into the crowded interior of a single brain cell. Inside that cell, threaded through it like the framework of a building, are the structures Stuart Hameroff staked everything on. They are called microtubules, and the name is honest because that is exactly what they are, microscopically small tubes. Each one is hollow, a slender cylinder about 25 nanometers across. Let me try to make that number mean something, because a nanometer is a measurement the human mind simply cannot picture on its own. A microtubule is roughly 3,000 times thinner than a single human hair. If you took one strand of hair from your head and split it lengthwise into 3,000 equal threads, one of those threads would be about the width of a microtubule. We are operating at a scale where ordinary intuition has nothing left to say. These tubes are not smooth like a drinking straw. They are built, brick by brick, from a protein called tubulin, and the tubulin proteins are arranged in a beautifully precise pattern, a lattice of 13 columns running the length of the tube, each protein locking against its neighbours in a tidy repeating grid. Picture a sheet of hexagons, the kind you see in a honeycomb, and now imagine rolling that sheet into a cylinder so the pattern wraps cleanly around. That is the architecture of a microtubule, a rolled lattice of identical units, orderly and exact in a way that is unusual for the messy interior of a living cell. And it is precisely that order, that clean repeating geometry, that made Hameroff's eyes light up. Chaos destroys quantum states. Order might just protect them. Let me give you the numbers, because the scale here is the kind of thing that should make you go quiet for a second. A single neuron can contain on the order of 1 billion tubulin proteins. 1 billion in one cell. And you have around 86 billion neurons. Multiply those together, and you arrive at a number of tubulins in the brain that lands somewhere around 100 billion. That is a 1 followed by 20 zeros. To put it in the kind of comparison this channel loves, that is roughly the same as the number of stars spread across tens of billions of galaxies. You are carrying, inside your head, a population of these tiny structures comparable to the star fields of a sizable chunk of the observable universe. The cosmos you are trying to understand tonight is, in a strange numerical sense, mirrored in the very organ trying to understand it. For most of the history of biology, microtubules were considered important, but frankly, unglamorous. Their known jobs are real and essential. They form the cytoskeleton, the internal scaffolding that gives a cell its shape and structure. They act as railways, the tracks along which little molecular motors haul cargo from one end of the cell to the other. And when a cell divides, microtubules are the ropes that pull the duplicated chromosomes apart into the two new cells. All of this is settled, textbook, undisputed science. Microtubules are the cell's skeleton, its highways, and its rigging. Nobody argues about any of that. What Hameroff proposed was something far more radical, and this is where the controversy begins. He suggested that the lattice is not only scaffolding, but also a kind of processor. Remember that each tubulin protein can flex between different physical shapes, can sit in one configuration or another. Hameroff proposed treating each of those configurations as a piece of information, a switch that can be set one way or the other, like a bit in a computer. A microtubule, in this view, is not just a structural beam, it is a dense lattice of millions of switches, an information processing device hiding inside every neuron, far below the level where neuroscience usually looks. And then comes the crucial leap, the one that turns this from clever to revolutionary. He proposed that each tubulin switch could sit not just in one state or the other, but in a quantum superposition of both at once. There is a reason microtubules, specifically, kept drawing attention, and it has to do with what they are made of. Tubulin proteins are unusually crowded with rings of carbon atoms, the kind chemists call aromatic, including a particular building block called tryptophan. These rings are special because they hold their electrons loosely, in clouds that can shift and respond, and do genuinely unusual things with light and electric charge. I want you to file that detail away carefully, because it is going to come roaring back later as a piece of real laboratory evidence. For now, just hold the thought that microtubules are not made of ordinary, electrically dull material. They are built from exactly the kind of stuff that, under the right conditions, can behave in ways that look more like physics than like plumbing. Here is a detail that Hameroff loves, and it is worth pausing on because it stretches the imagination in a useful way. Microtubules are not unique to brain cells, or even to animals. They exist in single-celled creatures, organisms like the paramecium, a tiny thing that swims around in pond water with no brain, no neurons, and not a single synapse anywhere in its body. And yet a paramecium hunts. It flees from danger. It can navigate a maze, and there is evidence it can even learn from experience, all without one nerve cell to its name. What it does have, in abundance, is microtubules. Hameroff points to this and asks a provocative question. What if the kind of information processing that underlies behavior, even something like primitive cognition, did not begin with brains at all, but began far earlier, inside these structures, in creatures that existed long before the first neuron evolved? I have to keep us honest here, the way I promised at the start. Nothing I have described so far is consciousness. None of it, on its own, is even quantum yet. So far, we have only a structure, a candidate, a proposed piece of hardware. We have a place inside the neuron orderly enough that a delicate quantum state might, in principle, be sheltered there. That is all. Mainstream neuroscience looks at the very same microtubules and sees plumbing, structural beams, and cargo rails, and nothing more. And for now, mainstream neuroscience has every right to. The gap between this is interesting hardware, and this is the seat of consciousness, is enormous, and the whole rest of tonight is really about whether anything can close it. But a piece of hardware, even a beautiful one, is only half a machine. A structure that can hold a quantum state is useless unless something makes that state do something, makes it resolve, makes it fire, makes it become a single, definite moment of experience. And this is where Roger Penrose supplied the other half, the part that came down from the mathematics of black holes and the bending of spacetime. Because his answer to what makes the quantum state collapse is, without exaggeration, the most audacious single idea in this entire theory, and possibly the most audacious idea about the mind that any serious scientist has ever proposed. To understand it, we have to leave biology behind for a while and talk about the strangest unsolved problem in all of physics. Is less than break time equals 1s, is greater than number, part 5. When gravity pulls the trigger. Let me take you to the edge of the deepest unsolved mystery in physics, the one that has haunted the field for a century, because the whole theory turns on it. In the quantum world, a particle does not have to be in one place or one state. It can be in many at once, spread across possibilities like a chord rather than a single note. An electron can be over here and over there at the same time, not because we do not know which, but genuinely, physically, both. This is not a quirk of our ignorance. It is how the smallest pieces of reality actually behave, confirmed by experiment after experiment for 100 years. And then something happens. The moment we look, the moment the particle interacts with the wider world, all those possibilities suddenly snap down into just one. The chord collapses to a single note. The electron is found in one place, and the others simply vanish. Physicists call this collapse, and here is the scandal at the center of it. Nobody knows what causes it. Nobody knows what counts as looking. This is what physicists politely call the measurement problem, and I want you to feel just how unfinished it really is, because most people assume it was sorted out long ago. The standard textbook approach, the one most students are taught, essentially says that collapse happens upon measurement and then waves a hand and moves on, but it never defines what a measurement is. Does a measurement require a conscious observer, a machine, a single stray particle bumping into the system? The theory that underpins all of modern technology, the most precisely tested theory in the history of science, has a hole right in the middle of it where the explanation of this one crucial step should be. We have equations that predict the odds perfectly. We have nothing that tells us why or when the dice actually land. Most physicists learn to live with this hole. They use the equations, get the right answers, and try not to lose sleep over the philosophy. But Roger Penrose refused to look away, and he made a break with convention so clean it is almost shocking. He proposed that collapse has nothing to do with observers at all. No conscious watcher is required, no measuring device, no human peeking. Collapse, he said, is a real physical event that happens out in the world entirely on its own, whether or not anyone is around to see it. It is objective, a feature of reality itself, rather than of our knowledge, and that is the second word in our theory's name, finally explained. Objective reduction. Reduction is just another word for collapse, the reduction of many possibilities down to one. Objective means it really happens, all by itself, as a fact of nature. So if no observer causes collapse, what does? This is where Penrose reached for the one force he had spent his life studying, the force that shapes the entire cosmos, gravity. To follow his reasoning, you only need to hold two ideas at once, and I will give them to you slowly. The first idea you already have. A particle can be in two places at once. The second idea comes from Einstein. Mass bends spacetime, the very fabric of reality, the way a heavy ball bends a stretched rubber sheet. Every object with mass creates a little dimple in spacetime around it, and that dimple is what we feel as gravity. Now put those two ideas together and watch what happens. If a particle is in two places at once, and the particle has mass, then it is bending spacetime in two different places at once. It is creating two contradictory dimples in the fabric of reality simultaneously. Penrose argued that spacetime cannot comfortably tolerate this. Reality, at its foundation, does not like holding two incompatible shapes of itself in the same instant. The two contradictory curvatures create a kind of instability, a tension in the fabric, and that instability cannot last. After a certain time, spacetime resolves the contradiction by collapsing the superposition down to one definite state, one location, one shape. The particle picks a place, not because anyone looked, but because gravity itself, the geometry of the universe, became unstable and had to settle. Gravity is the trigger. The bending of spacetime is what pulls it. Now, how long does this take? This is where the idea becomes genuinely beautiful, because Penrose did not just hand-wave. He gave a relationship, and while I promised no mathematics, the spirit of it is simple enough to feel. The time it takes for spacetime to collapse depends on how much of a contradiction is being held, on how much mass is separated, and by how far. A bigger mass difference means a bigger contradiction in spacetime, which means a faster collapse. A tiny contradiction can linger a long, long time. A large one resolves almost instantly. Collapse is not random in its timing. It is governed by gravity, by the scale of the disturbance in the fabric of the universe. Let me make that real with the kind of scale comparison that should make your mind tilt. Take a single electron, about as small a mass as there is, and hold it in superposition in two places at once, all by itself. How long before Penrose's gravitational instability collapses it? On the order of 10 million years. A lone electron could sit there, smeared across two possibilities, for a span longer than our entire species has existed, before gravity got around to forcing a decision. Now go the other way. Take a speck of dust, something just barely visible to your eye, and put it in two places at once. The collapse would happen in a tiny fraction of a second, almost instantly, because the dust is enormous compared to an electron and bends spacetime far more violently. So here is the picture. Tiny things can stay quantum for ages. Big things collapse at once. And somewhere between the lone electron and the speck of dust lies a sweet spot, a scale where collapse happens not in 10 million years and not in an instant, but in the fraction of a second that matches the rhythm of a thought. The theory claims the brain is built to operate right there, in that narrow band. And now I can finally tell you what the title of this video actually means, because we have assembled every piece needed to understand it, and it is not a metaphor. If Penrose is right, then every single collapse, every reduction of quantum possibility into one definite outcome, is an event in the geometry of spacetime itself. It is a small ripple resolved in the same fabric that holds galaxies in their orbits and bends starlight around the Sunday. Which means that if consciousness is made of these collapses, then each conscious moment is literally a tiny event in the structure of the universe. Not connected to the universe by poetry or feeling or wishful metaphor, but connected by physics, by the actual fabric of reality, folding and resolving inside your head. When you have a thought on this theory, the cosmos itself flexes, just slightly, just locally, and settles. That is the claim. That is what your brain being connected to the universe really means. I want to push the strangeness of this one step further, because it leads somewhere that should genuinely stop you. For over a century, physicists have searched for the holy grail of their field, a single theory uniting the quantum mechanics of the very small with the gravity that governs the very large. These two pillars of physics, both magnificently successful in their own domains, refuse to fit together, and finding where they finally meet is the great unfinished task of modern science. Most physicists assume the meeting place will be found in the most extreme corners of the universe, at the center of a black hole, or in the first sliver of a second after the Big Bang, places of unimaginable density and energy. Penrose's suggestion turns that expectation completely on its head. He proposes that quantum mechanics and gravity meet, and shake hands, and do their deepest work, not in a black hole at all, but here, in something soft and warm and close, in the dozens of small space-time collapses happening inside your skull every second of your waking life, the deepest secret of the cosmos, hiding in the most ordinary place imaginable. I have to set down the honesty flag again here, firmly, because this is exactly the kind of idea that is so beautiful you can forget to check whether it is true. Objective reduction is not established physics. It is a proposed solution to the measurement problem, one of several, and it has not been confirmed. Physicists are only just beginning to build experiments capable of testing whether gravity really does cause collapse the way Penrose says, and we will get to those experiments later tonight because some of them are actually pushing against his idea. So hold all of this lightly. What we have just walked through is not a fact about your brain. It is the most audacious proposal in the whole theory, the idea that the two greatest mysteries in science, the nature of consciousness and the unification of physics, might secretly be the same mystery. Whether that proposal survives contact with evidence is the question that will occupy the rest of our night. But even granting Penrose his collapse, even granting Hameroff his microtubules, we still do not have a mind. A trigger and a place are not yet a thought. We need to see how millions of these tiny collapses, scattered through billions of neurons, could be gathered up, coordinated, made to act as one, and woven into the single smooth river of experience that you are having at this very moment as you listen. That gathering, that coordination, is the first word in the theory's name, the word we have not yet touched, orchestrated, and it is where the whole strange machine finally comes to life. Is less than break time equals 1s, is greater than number, part 6, 40 windows a second. We have the place, the microtubules, and we have the trigger, gravity, pulling collapse out of superposition. Now we have to make a mind out of them, and that requires the first and most important word in the theory's name, the word orchestrated. Because a single tubulin protein flipping its state, even a whole microtubule collapsing, would be nothing on its own, a meaningless flicker, a single grain of sand. To produce the unified, flowing experience of a conscious moment, you would need enormous numbers of these quantum events, scattered across countless microtubules in countless neurons, to be linked together, coordinated, made to collapse not as a chaotic crowd of separate flickers, but as one single orchestrated event, like an enormous orchestra of instruments resolving onto a single chord at the same instant. So how would the brain manage that orchestration? This is where the biology and the physics have to cooperate, and it is the part of the theory that is least pinned down, so I will be careful. The proposal is that the brain's machinery, the proteins that coat the microtubules, the precisely ordered water molecules trapped along their surfaces, the clean geometry of the lattice itself, all work together to protect these fragile quantum states and to connect them, to shield them from the surrounding chaos long enough, and to link them across many neurons at once, so that instead of a billion isolated quantum events, you get one large, connected quantum state, spanning a whole population of microtubules. The word orchestrated is doing a great deal of heavy lifting in that sentence, and we will see shortly why critics have hammered hardest at exactly this point. But hold the picture for now. A connected quantum superposition spread across a region of the brain, growing, gathering, building, and then it fires. As that connected superposition grows, the amount of mass held in two places at once grows with it, and the contradiction in spacetime deepens, and the gravitational instability builds toward Penrose's threshold. When it crosses that threshold, the whole orchestrated state collapses all at once in a single objective reduction. And here is the claim that ties everything together, the keystone of the entire theory. That collapse, that one coordinated resolution of a brain-wide quantum state, is a single moment of conscious experience, not a representation of one, not a correlate of one. The collapse itself is the conscious moment. The flash of now that you are experiencing as you listen is, on this theory, the universe's geometry resolving an instability inside your head. Now, how often does this happen? The theory puts the rate at roughly 40 times every second, and this is not a number plucked from the air. The brain has a famous rhythm, a pattern of electrical activity oscillating at around 40 cycles per second, which scientists call gamma waves. And gamma waves have been linked, through decades of careful experiment, to conscious awareness, to the moments when scattered information seems to bind together into a single, unified perception. So the theory makes a bold move. It says these 40 per second collapses are the gamma rhythm that the brainwave neuroscientists have measured for years is the visible heartbeat of consciousness being assembled, one orchestrated collapse at a time, a real, measurable signal reinterpreted as the ticking clock of awareness itself. Let me make that rate something you can feel, because 40 times a second sounds fast, but stays abstract until you do the arithmetic. 40 conscious moments every second means about 2,400 every minute. Over a single hour of being awake, that is on the order of 144,000 separate discrete moments of experience. Your sense of a smooth, unbroken stream of consciousness, the seamless flow of your inner life, would actually be built from 144,000 individual frames every hour, each one a separate collapse, stitched together by the brain into the illusion of continuity. Your stream of consciousness, on this theory, is a flipbook, a very, very fast one. That comparison is worth dwelling on, because it reframes something you have felt your whole life. Think about how a film works. It is not actually moving at all. It is a sequence of still photographs, shown so quickly that your mind fuses them into smooth motion. The flow you see on the screen is an illusion built from discrete frames. Orr proposes that your consciousness works the very same way. The continuous river of now that feels so seamless, so unbroken, would in fact be a rapid procession of separate moments, each one a distinct quantum collapse, each one gone before the next arrives. And the smoothness you feel is your brain doing what it always does, filling the gaps, telling you a continuous story out of discrete events. The present moment, the most intimate and obvious thing in your entire existence, might be flickering 40 times a second, and you would never know. And here is where I want to tie every frame back to the cosmos, because this is the thread that holds our whole night together. If each of those 144,000 moments per hour is an objective reduction, then each one is the geometry of spacetime resolving a small instability, which means the same physics is at work in your quiet thoughts right now, as is at work when a moon settles into orbit, when light bends around a distant galaxy, when the universe at its largest scales does the slow work of gravity. The cosmos and the contents of your mind would be running on one shared mechanism, the same fundamental process, scaled all the way down from the architecture of galaxies to the inside of a single neuron. You would not be observing the universe from the outside. You would be a place where the universe performs, very locally and very quickly, the exact operation it performs everywhere else. I want to draw one sharp distinction before we move on, because people constantly confuse this theory with an older and much vaguer idea, and the confusion does real damage. There is a long-standing notion, popular in certain corners, that consciousness creates reality, that a conscious mind is what collapses the quantum wave function, that the universe needs an observer to become definite. That is not this theory. In fact, Or turns that idea completely upside down. It does not say that mind causes collapse. It says that collapse causes mind. The conscious moment does not reach out and force the universe to choose. The universe, through gravity, does the choosing all on its own, and the conscious moment is what that choosing feels like from the inside. The arrow points the other way. You are not the cause of collapse. You are made of it. So there it is, the whole machine, assembled at last, microtubules to hold the quantum states, biological orchestration to protect and connect them across the brain, gravity to pull the trigger when the threshold is crossed, and the collapse itself, 40 times a second, being the very stuff of conscious experience, each frame a small event in the fabric of the cosmos. It is, I think you will agree, an extraordinary structure of an idea, elegant and bold, and reaching from the smallest scales of biology to the largest questions in physics. But elegance is not truth, and boldness is not evidence. And for about 20 years, almost everyone who studied the brain believed this entire beautiful machine had been demolished by a single devastating calculation, a calculation that seemed to prove the whole thing was flatly, physically impossible. Before we can ask whether the theory deserves to be alive at all, we have to face that calculation head-on. We have to meet the argument that was treated For 2 decades, as the gravestone of quantum consciousness is less than break time equals 1s is greater than number part 7. The knockout punch. Everything we have built tonight rests on a single fragile assumption, and a good detective always attacks the weakest joint first. The entire theory depends on a quantum state surviving inside a neuron long enough to do something, long enough to grow, to orchestrate, to reach the threshold and collapse in a coordinated way. So the obvious question, the one any skeptical physicist would ask immediately, is brutally simple. Could a quantum state possibly survive in there at all? And in the year 2000, a physicist named Max Tegmark sat down and tried to answer that question with hard numbers, aimed like a rifle directly at the theory of quantum consciousness. What he found became, for the next 20 years, the single most quoted reason to dismiss the entire idea. To understand his attack, you need to understand the great enemy of all things quantum, a process with a slightly forbidding name, decoherence. Quantum states, those delicate superpositions where something is in many states at once, are almost unbelievably fragile. They are like a soap bubble, or a house of cards balanced in a doorway. The instant a quantum system touches its surroundings, the moment a single stray particle bumps into it, a photon, an air molecule, a vibration, the superposition leaks its quantum nature out into the environment and collapses into an ordinary, definite, classical state. This leaking is decoherence, and it is why we never see everyday objects in 2 places at once. The world is constantly touching them, measuring them, knocking them out of their quantum haze faster than we could ever notice. To keep a quantum state alive, you have to isolate it almost perfectly, which is why physicists who build quantum computers go to extraordinary lengths, chilling their machines to within a hair of absolute zero and shielding them from every possible disturbance. And now look at the brain, and you begin to see the problem Tegmark pointed at. The brain is just about the worst possible place to try to keep a quantum state alive. It is warm, sitting at body temperature, full of thermal energy, with molecules jostling and colliding constantly. It is wet, soaked in salty fluid, full of charged particles, crashing around in every direction. And it is electrically noisy, roaring with activity, the very opposite of the silent, frozen, isolated chambers where quantum computers have to live. Physicists summarize the objection in 3 words that have become almost a slogan, repeated in lecture halls whenever the subject comes up. The brain is warm, wet, and noisy. It is, by this argument, the most hostile environment imaginable for anything quantum. Tegmark put numbers to it, and the numbers landed like a verdict. He calculated how long a quantum superposition could last in the conditions inside a neuron before decoherence destroyed it, and his estimate was something like 10 to the minus 13 seconds. That is a 1/10 of a trillionth of a second. Meanwhile, the events that matter for thought, the firing of neurons, the rhythms of the brain, the orchestrated collapses the theory needs, unfold over something like a 1/10 of a second. Lay those 2 numbers side by side, and the gap is staggering. The quantum state, by Tegmark's reckoning, would die roughly 1 trillion times faster than it would need to survive in order to play any role in consciousness at all. It would be gone before it had even begun. Let me make that trillion-fold gap something you can actually feel, because 1 trillion is another of those numbers the mind slides right off. Imagine you need a candle to stay lit for a certain task. The task takes 30,000 years to complete, and your candle, no matter what you do, burns out after a single second. That is the scale of the mismatch Tegmark calculated. The quantum state needs to last long enough to matter, and instead it vanishes almost infinitely sooner, like that candle guttering out a heartbeat after you light it, while the work it was meant for stretches across the age of civilizations. By this argument, asking microtubules to sustain a useful quantum state, is not just difficult. It is off by so many orders of magnitude that it looks not merely unlikely, but impossible. This calculation did tremendous damage, and it is important to understand why. For the next 2 decades, Tegmark's result became the standard one-line refutation, the thing a busy neuroscientist could say to wave the whole theory away without having to engage with any of its details. Quantum effects cannot survive in the warm, wet brain. End of discussion. Next question. The idea of quantum consciousness was filed away by most of the scientific community as a beautiful mistake, the kind of thing a brilliant physicist like Penrose might wander into when he strays too far from his home territory, but not something a serious brain scientist needed to take seriously. The gravestone had been carved, and the calculation was the inscription. I want to step sideways for a moment here, because to judge this fight fairly, you need to understand something more fundamental, something about why collapse is mysterious in the first place. We have been talking about collapse all night, as if physicists understand it, but I told you earlier they do not, and this is the place to face that squarely. When a quantum superposition becomes a single definite outcome, physics genuinely cannot agree on what is happening, and the disagreement runs so far down that it has split into rival worldviews, each one a different answer to the same impossible question. These are called interpretations of quantum mechanics, and they are not minor technical quibbles. They are radically different pictures of what reality is. There is the old standard view, often called the Copenhagen interpretation, which essentially says that collapse happens when a measurement is made and instructs you not to ask what is really going on underneath, to just use the equations and be quiet. There is the many worlds interpretation, which makes the dizzying claim that the collapse never actually happens at all, that every possibility comes true, each in its own branching universe, so that reality is endlessly splitting into parallel copies, one for every outcome that could occur. And then there is the family of ideas that Penrose belongs to, the objective collapse theories, which insist that collapse is a real physical event, something that genuinely happens out in the world, and which therefore must have a real physical cause. I want you to notice something about Penrose's camp, because it is to its enormous credit. Of all these interpretations, the objective collapse theories are among the very few that make predictions you can actually test, that say collapse will behave in a specific, measurable way. Many worlds and Copenhagen are, in a sense, unfalsifiable. Penrose stuck his neck out and proposed something nature could prove wrong. So that is the strange backdrop to Tegmark's attack. The thing being attacked, collapse, is itself a thing physics does not understand. And into this confusion, the defenders of quantum consciousness fired back. In 2002, 3 researchers, Hagen, Hameroff, and Tosinski, published a rebuttal arguing that Tegmark had made his calculation with the wrong assumptions. They claimed he had modelled the geometry of the quantum state incorrectly, had gotten the distances and the arrangement wrong, and that when you corrected the model and accounted for the ways biology might shield a quantum state, with ordered water, with the screening of electric charges, with the protective structure of the lattice itself, the survival time could be far longer than Tegmark's 1/10 of a trillionth of a second. Long enough, they argued, to possibly matter after all. But I have to be scrupulously fair here, because this is exactly the kind of moment where it is tempting to declare a winner and move on. The rebuttal did not prove the theory was right. It did not vindicate quantum consciousness. All it did was keep the patient breathing. It showed that Tegmark's calculation was not the airtight, final, case-closed refutation it had been treated as, that there was room to argue about the assumptions, that the gap might be smaller than it first appeared. The disagreement became a standoff, 2 camps with 2 sets of calculations, each accusing the other of modelling the situation wrong, and a standoff of dueling calculations can go on forever. Theorists can argue assumptions until the end of time. The only thing that could ever truly break the deadlock was not a better argument. It was evidence, real evidence, from the laboratory, and it would have to come from a direction nobody was expecting. Because here is what hangs on this, and I want to bring it all the way back to the thread before we move on. The decoherence objection is not some side detail, some technical footnote. It is the exact hinge on which our entire title swings. If a quantum state cannot survive in the brain, then there is no orchestrated collapse, no 40 windows a second, no thought woven into the fabric of spacetime, and the beautiful machine we spent the last hour building simply falls apart in our hands. The whole claim that your brain is connected to the universe lives or dies on whether warm, wet biology can do something physicists were once certain it could never do. So everything now depends on a single question. Can life, somehow, against all expectation, keep a quantum state alive in the warmth and the wet and the noise? And the answer, when it came, arrived not from brain science at all, but from a leaf and a bird and the everyday machinery of life itself. Is less than break time, equals 1s, is greater than number, part 8, but life already cheats. While the physicists were locked in their standoff, arguing back and forth about whether biology could ever, even in principle, sustain a quantum state, something quietly remarkable was happening in a completely different corner of science. Biologists were discovering that the question was not really hypothetical at all. Life, it turned out, was not waiting for permission. Warm, wet, noisy living things were already using quantum effects, right out in the open, in processes so common and so essential that they power much of the living world. A whole new field grew up around this discovery, and it has a name that would have sounded like a contradiction in terms not long ago: quantum biology, and it changed the entire weather around the question of quantum consciousness. Start with the most fundamental process there is, the one that feeds nearly everything alive: photosynthesis. When a plant or a bacterium captures sunlight, it has to take the energy from an incoming particle of light and shuttle it across a forest of molecules to a reaction center, where the energy gets put to work. And for a long time, the efficiency of this process was a genuine puzzle, because the energy reaches its destination almost without loss, with an efficiency that seemed too good for a blind molecular relay race to achieve. Then experiments revealed something astonishing. The energy does not simply bounce from molecule to molecule, trying one path at a time like a marble in a maze. It appears to explore many possible paths at once, in quantum superposition, sampling all the routes simultaneously and effectively finding the most efficient one. Inside a leaf, at ordinary temperatures. In the warm and the wet, the very conditions Tegmark said would destroy any quantum effect almost instantly. Sit with that for a moment, because it is the crack in the wall. The process that underlies nearly all life on this planet, the green machinery that turns sunlight into food and oxygen, the foundation of almost every food chain there is, may lean on precisely the kind of quantum coherence that the decoherence objection said was impossible in biology. Every blade of grass, every tree, every drifting ocean plankton would be running a quantum trick in plain daylight, in warm tissue, billions of times over, all around the world, all the time. Whatever certainty there once was about biology being too hot and messy for quantum effects, the humble leaf had already quietly broken it. But photosynthesis is not the only example, and the next one is, if anything, even harder to dismiss, because it involves not just energy efficiency, but a delicate quantum relationship surviving inside a living animal. Consider the European robin and the mystery of how migratory birds navigate. Many birds can sense the Earth's magnetic field and use it like a compass to find their way across entire continents, returning year after year to the same patch of ground. For decades, nobody could explain how a living creature could possibly detect something as faint as the planet's magnetic field. The leading explanation now is frankly stunning. It involves a quantum effect called a radical pair. When light strikes a particular protein in the bird's eye, it creates a pair of electrons whose quantum states are entangled, linked together in that spooky quantum way, where they behave as a single connected system, even when separated. And the precise behavior of this entangled pair is sensitive to the angle of the Earth's magnetic field, which means the bird can, in effect, see the magnetic field, read it off the quantum state of electrons in its own eye. Let that fully register. Because of everything in quantum biology, this may be the most direct answer to Tegmark's objection. A bird's eye is warm. It is wet. It is biologically noisy, just like a brain. And yet the evidence suggests it maintains a quantum entanglement long enough and stably enough to extract usable navigational information from it, long enough to steer the bird across an ocean. If a robin's eye can shelter an entangled quantum state in warm, wet tissue and put it to work, then the blanket claim that warm, wet tissue makes quantum effects useless is simply no longer safe. Nature found a way. Evolution, given hundreds of millions of years to work, apparently learned to protect and exploit the very coherence physicists thought biology could never hold. And there is more, woven through the ordinary chemistry of life. Some enzymes, the molecular machines that drive the reactions keeping you alive, appear to use a quantum effect called tunneling, where a particle passes straight through an energy barrier that, by the rules of ordinary classical physics, it should not have enough energy to cross. It is as if a ball, lacking the energy to roll over a hill, simply appeared on the other side. This quantum tunneling of protons and electrons is now accepted as part of how certain enzymes achieve their astonishing speed, and it has even been proposed as part of how your sense of smell works, with the nose perhaps detecting not just the shape of a molecule, but the quantum vibrations within it. Quantum effects, in other words, are not some exotic rarity reserved for laboratories. They appear to be threaded through the everyday machinery of being alive. So the reframing this forces on us is profound, and I want to state it carefully. The objection that quantum effects cannot survive in warm, wet, noisy biology is not just weakened. It is, in its blanket form, demonstrably wrong. Biology does sustain functional quantum effects in leaves, in birds' eyes, in enzymes, at body temperature, in the wet and the noise. Evolution has found ways to shelter coherence, to protect these states from decoherence long enough to put them to use. The question is no longer whether warm biology can do anything quantum. We know it can. The question has narrowed to something much more specific. Can the brain in microtubules do it too, and at the scale and in the way that consciousness would require? I have to slam on the honesty brakes here, hard, because this is exactly the kind of moment that gets oversold, and I will not do that to you. None of these examples is consciousness. A photosynthesizing leaf is not having an experience. A robin navigating is not pondering its own existence. And crucially, not one of these quantum biology effects involves Penrose's gravitational collapse, his objective reduction. They are different quantum phenomena entirely, coherence and entanglement and tunneling, not the specific space-time-driven mechanism the theory of consciousness depends on. What quantum biology proves is possibility, not the theory. It knocks down the wall that said this whole idea was impossible. It does not build the house on the other side. Those are very different things, and confusing them is how good science turns into bad hype. But there is one more detail from quantum biology that is going to send a shiver down the thread we have been following all night, and it is the reason I told you to file away a particular fact back when we were inside the cell. Remember those electron-crowded molecules I mentioned? The aromatic rings, the tryptophan, packed densely into the tubulin that builds microtubules? It turns out that these very molecules, tryptophan and its cousins, are central players in several of the quantum biology effects scientists have been studying. The same kind of structure that lets a leaf or an enzyme do its quantum trick is exactly the kind of structure crowded into microtubules. So the microtubule is not made of quantum dull material. It is built from precisely the sort of stuff that, elsewhere in biology, has already been caught behaving quantum mechanically. That is why microtubules keep surfacing, again and again, no matter how many times the theory is declared dead. So let me bring this back to where it has to go, back to the thread that holds our night together. Quantum biology does not prove that your mind is woven into the fabric of spacetime. It does not show that gravity collapses superpositions in your microtubules 40 times a second. What it does is far more limited and far more important than that. It demolishes the one argument, the single calculation, that for 20 years said the whole idea was flatly, physically impossible. It reopens the courtroom. It takes the gravestone and tips it over, and it puts the burden of proof back where it belongs, on the search for direct evidence, evidence not from a leaf or a bird, but from the brain itself. And in the last few years, that direct evidence has finally started to arrive, from experiments aimed straight at the question, and not all of it has gone the way the skeptics expected. Is less than break time equals 1s is greater than number. Part 9. The evidence nobody expected. For decades, the theory of quantum consciousness lived almost entirely in the world of argument, of dueling calculations and thought experiments and philosophical sparring. What it lacked, what it desperately needed, was experiments aimed directly at the brain, tests that could put real numbers on the table instead of competing assumptions. And in the last few years, with the impossible objection weakened by quantum biology, researchers finally started running those experiments. The results are not a confirmation of the theory, and I am going to keep reminding you of that, but they are also not nothing. Several of them point, tentatively, in a direction the skeptics did not expect, and that is genuinely interesting, whatever it ultimately turns out to mean. Start with the experiment that has done the most to drag this theory back into serious conversation, and it brings us right back to Stuart Hameroff's original obsession, anesthesia. In 2024, a team of researchers at Wellesley College published a study in a journal called eNeuro, and the design was elegant in its simplicity. They reasoned like this. If consciousness depends on microtubules, the way the theory claims, then doing something to stabilize those microtubules, to make them sturdier and harder to disturb, ought to make consciousness harder to switch off. So they took a drug called epopholone B, which is known to bind to microtubules and stabilize them, and they gave it to rats. Then they anesthetized those rats, and they measured one simple thing. How long did it take each rat to lose consciousness? The result was small, but it was real, and it was statistically significant. The rats whose microtubules had been stabilized took, on average, about 69 seconds longer to go under than the untreated rats. Let me make sure that lands properly. Stiffen the microtubules, and consciousness clings on longer, resists the anesthetic, takes more than a full extra minute to let go. And the researchers were careful, ruling out the obvious alternative explanations, checking that it was not simply tolerance building up from repeated exposure to the anesthetic. The cleanest reading of the result is that the anesthetic acts on microtubules to produce unconsciousness, which means microtubules are plausibly part of the very switch that turns consciousness off and on, exactly as the theory predicted. Now, I have to be honest, as always, this does not prove quantum collapse. It does not show gravity doing anything in a neuron. What it shows is that microtubules are tangled up in consciousness in a real, measurable way, which is a necessary first step for the theory and a genuine point in its favour. The second piece of evidence reaches right back to that detail I keep circling, the electron-crowded molecules inside tubulin. Also, in 2024, A study in the Journal of Physical Chemistry B reported something remarkable about networks of tryptophan, the very molecule packed into microtubules. They found evidence of a phenomenon called superradiance. Superradiance is a genuinely quantum, genuinely collective effect, where a group of molecules emit light together in a coordinated burst far more intensely than they would if each acted alone, because their quantum states have become linked. And the researchers found this collective quantum behavior in large networks of tryptophan arranged in lifelike conditions. Why does that matter for us? Because superradiance is exactly the kind of warm temperature collective quantum effect that Tegmark's objection said should be impossible, and they found it in precisely the molecule, in precisely the arrangement that microtubules are built from. The right effect, in the right material, in the right structure. Now I come to the boldest claim of all, and also the most contested, and I want to handle it with the most care of anything I say tonight, because it is the kind of result that is either historic or mistaken, with very little room in between. Beginning around 2022, a group of researchers at Trinity College Dublin reported something extraordinary. Using a clever technique based on magnetic resonance imaging, the same basic technology as a hospital MRI scan, they looked for signs of quantum entanglement inside living human brains. The logic was subtle, drawing on the idea that if two systems both become entangled with a third intermediary, you can sometimes detect that the intermediary was behaving quantum mechanically. And they reported signals that, on their interpretation, were consistent with entanglement between proton spins in the water of the brain, signals that were correlated with the heartbeat, and, intriguingly, with short-term memory performance. If that result is real, and that is an enormous if, it would be one of the most important findings in the history of brain science, a direct signature of quantum behavior in a living, thinking human brain. But I have to be absolutely clear about the uncertainty, because here is where hype does the most damage. The interpretation of that experiment is genuinely disputed. Many physicists are not convinced that the signals mean what the researchers think they mean, and there are alternative explanations that do not require any entanglement at all. Replication and confirmation are still pending. So, I am not telling you that quantum entanglement has been found in the human brain. I am telling you that a careful group of scientists has reported signals they believe are consistent with it, that the claim is on the table, and that it is being argued about right now. That is the honest state of it. Tantalizing, unconfirmed, and very much alive as a question. There is one more strand worth mentioning, the work of a researcher named Anirban Bandyopadhyay, who has reported that microtubules ring with electromagnetic resonances at specific, discrete frequencies across an enormous range, from kilohertz up through megahertz and into gigahertz. If that holds up, it is the kind of thing that could provide a mechanism for the orchestration the theory needs, a natural clock, a set of nested rhythms that could coordinate quantum activity across many microtubules at once, like the beats of a fractal metronome buried in the lattice. This work is provocative and only partially replicated, so file it, again, under interesting but unsettled. The pattern, by now, should be familiar. Let me say the crucial distinction one more time, because it is the most important sentence of the entire night, the thing that separates honest fascination from credulous nonsense. There is now real, accumulating evidence of non-trivial quantum effects in microtubules and in the molecules that build them. Superradiance, energy transfer, the anesthetic connection, strange resonances. That much is increasingly hard to dismiss. But there is not yet any direct evidence of quantum computation happening in a living brain, and there is not yet any direct evidence of Penrose's gravitational collapse events occurring in a neuron. The distance between quantum effects exists in microtubules, and consciousness is orchestrated, quantum collapse remains wide. And every honest researcher in this field keeps that distance firmly in view. The evidence has moved. It has not arrived. And here is a final twist that shows you this is real science and not just a faith, because real science can be proven wrong, and this idea is being tested in exactly that spirit. Penrose's specific claim about gravity causing collapse makes a precise prediction. If a quantum superposition really does collapse because of a gravitational instability, that collapse should release a tiny, faint burst of radiation, a specific signature you could, in principle, detect. And physicists have built experiments, some of them buried far underground, to shield them from interference, to hunt for exactly that radiation. The early results have not confirmed Penrose. In fact, they have started to put pressure on the simplest version of his model, constraining it, pushing against it, possibly even ruling parts of it out. I find that genuinely reassuring, in a strange way. It means we are not dealing with an unfalsifiable fantasy. We are dealing with a real scientific claim that nature is allowed to reject, and may yet reject. The theory has stuck its neck out, and the guillotine is real. So suppose, just for tonight, just as an exercise in following an idea to its end, that the evidence keeps tilting the way some of these recent experiments hint. Suppose the microtubules really are doing something quantum, and suppose, against the odds, that Penrose turns out to be right about gravity and collapse. What would it actually mean? Not as poetry, not as comfort, but concretely. What would it mean for you, lying here in the dark? What would it mean for the question of whether a machine could ever truly think, or whether you are genuinely free, or for the relationship between the universe and the strange small minds it has somehow produced inside itself? That is where we turn next, into the consequences, and they are large enough to be worth losing a little sleep over. Is less than break time equals 1s? Is greater than number, part 10, if it's true? I want to frame this whole part with a single, small word, and I want you to keep it glowing in your mind the entire time, because it is the word that keeps us honest. The word is if. Everything I am about to say lives under that word. We are not asserting any of this. We are following a thread to see where it leads, walking the consequences of a theory that may yet be wrong, the way you might follow a path in a dream just to see where it goes. So, if the theory is true, what follows? The answers turn out to touch some of the largest questions facing us right now, which is part of why this obscure debate about tiny tubes inside neurons refuses to stay in its corner. Begin with the question of our age, the one in every headline, the one that may define this century. Could a machine ever truly become conscious? Could an artificial intelligence, however powerful, ever genuinely wake up and have an experience of its own, rather than merely simulating one from the outside? On the standard view, the one most computer scientists hold, the answer is yes in principle, because consciousness is just a pattern of information processing, and a pattern can run on anything, on neurons or on silicon, it makes no difference. But if Penrose and Hameroff are right, the answer flips completely. If consciousness requires a specific physical process, quantum collapse driven by gravity in a particular biological structure, then no classical digital computer, no matter how enormous, how fast, how convincingly it talks, could ever actually be conscious. It would forever be a simulation of a mind without an inner life, a perfect imitation with nobody home, the philosopher's dream of a thing that acts conscious while experiencing precisely nothing. And notice that the reverse is just as loaded, which is what makes this a genuine fork rather than a settled matter. If the mainstream classical theories are correct instead, if consciousness really is substrate-independent computation, then machine consciousness is not only possible, it may be coming, and we will have to grapple with the staggering ethical weight of having created beings that can suffer and feel. So this quiet technical argument about microtubules and gravity sits, almost unnoticed, directly underneath one of the most consequential questions our species has ever had to face. The answer to whether our machines can wake up may depend on whether the thread we have been following tonight is real. That is not a small thing to be uncertain about. Then there is the ancient question, the one philosophers have wrestled with for thousands of years, the question of free will. Here, the picture has always seemed bleak from both directions. If the brain is a classical machine, then every thought and choice is just the inevitable result of the prior state of your neurons. Physics unfolding like clockwork, and there is no real freedom anywhere, only the illusion of it. But adding mere randomness does not help, because a choice made by a coin flip is no freer than a choice made by clockwork. Penrose and Hameroff suggest that objective reduction might offer something that is neither rigid determinism nor blind randomness, but a third thing, a non-computable process that is genuinely undetermined, yet not merely random, something that might leave a crack of room for what we mean by real choice. I will flag this loudly as the most speculative and philosophically contested corner of the whole theory, far out past the evidence. But it is part of why the idea grips people so tightly. It seems to offer a physics in which you might actually be the author of your own thoughts. And then there is the consequence that ties straight back to the title, the one that genuinely staggers me when I sit with it. Physics has spent a century searching for the union of its two greatest theories, quantum mechanics and gravity, the marriage that would complete our picture of reality. We have assumed that union, if we ever find it, will be glimpsed in places of cosmic extremity, the crushing center of a black hole, the first instant of creation. But if Orr is right, then quantum mechanics and gravity are meeting and working together right now, continuously, in the warm, soft tissue between your ears, 40 times a second, in every waking moment of your life. The deepest unsolved problem in physics would be solving itself, quietly and constantly, inside the very organ trying to solve it. Consciousness would not just be connected to the universe. Consciousness would be a window onto the most fundamental law of the cosmos, a place where you could, in principle, watch quantum gravity at work simply by paying attention to the fact that you are paying attention. This is what your brain, being connected to the universe, would really mean, stripped of all poetry. Not that you feel one with everything in some soft and pleasant way, but that the same precise physics resolving instabilities in spacetime across the entire universe, the physics that settles a moon into orbit and bends the light of distant galaxies, is the identical physics resolving each of your thoughts. One mechanism, scaled from the architecture of galaxies all the way down to the inside of a single cell. You would not be a spectator watching the cosmos from some separate vantage point. You would be a small region where the cosmos performs, locally and very quickly, the same operation it performs everywhere, and where, uniquely, that operation feels like something from the inside. There is a kind of humbling symmetry in this that I cannot quite shake. The universe spent 13.8 billion years cooling and clumping and building, assembling atoms into stars, and stars into galaxies, and a thin film of chemistry on at least one small planet into structures complex enough to look back out at all of it and ask what it is. And on this theory, that looking back, that wondering, uses the universe's own most fundamental machinery to do the wondering. The cosmos would have grown, after all those billions of years, an organ for asking about itself, and the asking would run on the same fundamental physics as the thing being asked about. Whether or not the theory survives, there is something almost unbearably strange in even being able to pose it. But I have kept that little word, if burning this entire time for a reason, and now I have to honour it. Every single consequence I have just walked you through hangs from an unproven claim, a theory that real experiments are right now trying their best to disprove. This has been an exercise in wonder, not a statement of fact, and the difference matters more here than almost anywhere. Because precisely when an idea is this beautiful, this sweeping, this flattering to our sense of cosmic importance, that is exactly the moment a careful mind should grip the railing of evidence the hardest. And there are people who have let go of that railing entirely on this very subject, who have taken this theory and run with it far past anything the science can support. To keep faith with you, I have to walk us right up to the line where the careful thinking ends, and show you exactly where it gives way to wishful thinking, is less than break time equals 1s, is greater than number, part 11, where the map runs out. A good guide does not only show you the country that has been mapped. A good guide also walks you to the edge of the map and points at the blank space beyond it and says, plainly, here is where the knowing stops and the guessing begins. This subject has such an edge, and it is a bright and important one, and I would be failing you if I let the beauty of the theory blur it. So let us walk to that edge together and look honestly at what lies past it, because some genuinely lovely and genuinely unsupported ideas live out there, and you deserve to know which is which. The first thing waiting past the edge is an idea called panpsychism, and it is ancient, and it is intriguing, and it is not science. The reasoning goes like this. If a conscious moment is tied to an objective reduction, a collapse event in spacetime, and if such collapse events happen all over the universe, not just in brains, then perhaps a tiny flicker of proto-experience, some faint seed of what it is like to be something, accompanies every collapse everywhere. Perhaps consciousness, in some primitive form, is not produced by brains at all, but is woven into the fabric of matter itself, present in the smallest grain, and brains merely gather it and concentrate it into the focused awareness we know. It is a haunting thought, and you can see how naturally it grows out of the theory. But I want to be clear, it is philosophy, not physics. There is no experiment that tests it, no measurement that could confirm or deny it. Mark it as a beautiful speculation, and hold it at exactly that distance. The second thing past the edge is closer to home, and more emotionally charged, and I have to be especially careful with it. Stuart Hameroff himself has speculated, in popular talks and interviews, that something might survive the death of the body. The idea he has floated is that the quantum information held in the microtubules might not simply be destroyed when the brain dies, but could dissipate outward into the universe, perhaps persisting in some form. And I understand completely why that idea is magnetic, why it would spread, why people would want it to be true. It speaks to the oldest hope there is. But here is the line, drawn as kindly and as firmly as I can draw it. This is Hameroff's personal speculation. It is not a result of the theory. The science of or neither requires it nor supports it, and it has been heavily criticized by other scientists, including some sympathetic to the underlying theory. The careful claim and the comforting fantasy built on top of it are two completely different things, and they must not be allowed to wear the same coat. I think it is worth pausing to ask why this particular theory attracts so much overreach, more than most ideas in science, because understanding that protects you. The answer is simple. A theory that connects the human mind to the cosmos is emotionally irresistible. It touches our longing to matter, our fear of death, our hope that we are more than a brief chemical accident on a small planet, and that very magnetism is the danger. The more an idea flatters our deepest wishes, the more tightly we should hold to the evidence, because that is exactly when we are most likely to believe something because we want it to be true rather than because it is. The pull you feel toward the grander versions of this story is real, and it is human, and it is precisely the thing to be most suspicious of. Because here is the thing, and it is the quiet truth at the bottom of all the speculation. The disciplinings of this wonder needs no embellishment whatsoever. Forget surviving death. Forget consciousness in every grain of sand. The genuinely astonishing fact, the one that is not speculative at all, is sitting right here, already, in your own skull. A little over a kilogram of warm, wet tissue, built from ordinary atoms forged in dead stars, somehow produces an entire inner universe, a felt world of color and sound and memory, and the strange certainty that there is a you in here, experiencing it all. That, with no theory required, is already the most profound mystery we know of anywhere in the cosmos. You do not need to gild it. You are the gilding. So let me bring this back to the thread one final time, because keeping the real claim separate from the fantasies stacked on top of it is the whole discipline of tonight. The actual theory on trial is narrow and specific and testable. It says quantum superpositions form in microtubules, that gravity collapses them when they cross a threshold, that this happens around 40 times a second, and that each collapse is a moment of experience. That is the claim. That is what the experiments are probing. Everything else, the surviving souls, the conscious universe, the cosmic oneness, is decoration draped over the structure by people who could not resist. And honoring how strange the true question really is, means refusing the decoration and looking clearly at the structure itself. So where does all of that leave us, lying here in the dark, somewhere between a Nobel laureate's equation and an experiment on a sleeping rat? It is time to gather everything and see what we are actually left holding is less than break time, equals 1s, is greater than number, part 12. The door that won't quite close. Let me give you the verdict of our trial, honestly, the way I promised at the very beginning. Orchestrated objective reduction is unproven. It remains a minority view, held by a small number of researchers against the skepticism of most of neuroscience, and it may yet be ruled out entirely by the very experiments now testing it, the ones hunting underground for the radiation Penrose's collapse should produce. If you came tonight hoping I would tell you that science has discovered your mind is one with the universe, I have to send you to sleep without that. The honest answer is that we do not know, and the careful answer is that the theory is probably facing an uphill climb against the experimental evidence. But I want you to notice what has actually happened here, because it is remarkable in its own right, evidence or no. A theory that was declared dead, buried under a single calculation for 20 years, dismissed with a one-line slogan about warm, wet brains, has climbed back out of its grave. And it did not come back because someone made a cleverer argument. It came back because of evidence, real evidence, arriving from directions nobody anticipated. A leaf doing quantum tricks in sunlight, a bird steering by entangled electrons in its eye, a rat clinging to consciousness 69 seconds longer because its microtubules were stiffened, the right molecule glowing with collective quantum light in a laboratory dish. None of it proves the theory. All of it means the question is alive again, genuinely open, being argued by serious people with real instruments, when not long ago it was considered closed and a little embarrassing to raise. That is not nothing. In science, reopening a question that was thought to be settled is sometimes the most important move of all. So let me restate the thread one last time, the spine that has held our whole night together. Whether or not gravity really is pulling the trigger 40 times a second behind your eyes, whether or not your thoughts are small events in the fabric of spacetime, the question that this theory tries to answer has not gone anywhere, and no one has answered it. How does a physical brain, an arrangement of ordinary matter obeying ordinary laws, produce a felt inner world? How does the water and the salt and the chemistry add up to the experience of being someone? That question is still standing, unanswered, in the middle of the most successful era of brain science in history. And the fact that we had to seriously consider an idea this strange, an idea reaching all the way down to quantum gravity just to take a swing at it, tells you how genuinely hard the question is. And here is the takeaway that survives even if OR falls tomorrow, even if every experiment turns against it, the thing I most want you to carry into sleep. The old, comfortable wall we build in our minds, the one with mind in here on one side and universe out there on the other, is far thinner and far stranger than common sense insists. Whatever consciousness turns out to be, it is not floating free above the physical world, and it is not separate from the cosmos that produced it. It is made of the same atoms, governed by the same laws, born from the same 13.8 billion year story as the stars. The only real question is just how directly the inside of your mind is wired into the inner workings of everything else, and tonight we have seen that the most serious attempt to answer that question wires it in about as tightly as it could possibly be. So return with me, one last time, to where we started, the thought you were having when this began, that quiet inner voice, that faint sense of a you behind your eyes. Was it only chemistry, signals racing along wet biological wires in the dark? Or was it, just possibly, the cosmos itself, in one small, warm place, briefly resolving its own geometry into the experience of being you? I cannot tell you which. Nobody can, not yet. And there is something I find perfect about lying down to sleep beside an open question that large, rather than a closed and tidy answer. You do not have to settle it tonight. You do not have to settle it ever. You can simply lie here, a small, warm knot of the same universe you have spent your whole life looking up at, holding a question that the universe has not yet managed to answer about itself. Because in the end, that may be the strangest fact of all, stranger than any theory, stranger than gravity, or quantum collapse, or any of it. After 13.8 billion years, the universe has somehow produced something that can lie awake in the dark and wonder where its own awareness comes from. Whatever the answer turns out to be, the wondering is already a kind of miracle. And it is a very good thing to fall asleep beside.